Hi, I'm Ben-Yaakov. This presentation is entitled Constant On-Time Control of PWM Converters, an Intuitive Explanation. Please note that the controller shown in this presentation is for educational purposes only. There is no endorsement or recommendation of this particular controller, and please be advised that there are constant on-time controllers which are made by other manufacturers. So what is constant on-time control? We can illustrate it in a simple way by this buck converter. Here we have a buck converter. This is the inductor, capacitor, and load. Here's the switcher. We have a diode. We have here the pulses coming in. And now suppose we have a step at the input going up. In the conventional or classical duty cycle modulation scheme, we're going to see the following. After the change, we're going to see a shorter on time, and so therefore the duty cycle becomes smaller because V in is larger, and I'm assuming, of course, a closed loop operation, that is V out is kept constant. To keep it constant with the higher V in, you need to reduce the duty cycle. In the case of a constant on time, the classical constant on time, what we're going to see here is a constant on time. And after the change, the next pulse will be farther away, so the period will be longer, so therefore the frequency is lower, and therefore the effective duty cycle is smaller, exactly as here, but while here the on time is becoming smaller, here it is maintained to be the same. This is assuming, of course, closed loop operation. And I'll show later on that there are some ways to sort of overcome this disadvantage of lower frequencies, because as the voltage will be higher and higher, of course, the frequency will go lower and lower, and this is something which is not very desirable. So there are ways, and I'll show it, to keep the frequency fairly constant in the case of a V in change, okay? So we'll talk about it a little bit later. So what happens in this type of a control if there is a step at the output that is a load step, okay? There's a current change going up in this case. So what we're going to see is, as the change is occurring here at this transition, the pulses of the gate, and therefore here at the switching point, are going to be sort of crowded more, and the frequency, of course, will be higher, so therefore the effective, you might say, duty cycle is larger, and this will cause the current to go up. So what we're going to see here is, initially, as the change is occurring, then there's going to be sort of a drop at V out, but at this point the current of the inductor is start to ramping up. Here it is, and consequently it'll sort of correct this drop, and eventually will come to the same value, of, assuming, of course, that the system is working in closed loop. I'm talking about closed loop operation. I'm not showing it here at this point. So this is sort of the average behavior of the system. Now, in practice, what is done is that the control is accomplished by a hysteresis type control. That is, we rely on the ripple at the output, and as the output goes down and reaches the reference value, this will kick, and then the one shot will produce a pulse that through the driver is delivered to the transistor. So this is a very simple kind of control, of course, and as it turns out, and I'll discuss it a little bit more later on, although I'm not going to dwell into it too much, there is no need for phase compensation here. This is a sort of a, you might say, bang-bang control, hysteresis control, which is stable by itself. Now, normally we're going to have an on time, then an off time, but these systems are built in such a way that as you increase here the magnitude, say, of the current, you might say, or the average voltage, then the off time becoming smaller and smaller, and then there is a limit. There's a T-off minimum that the system will not reduce the off time below that. Now, it is important to realize that no matter what is the control, as long as we are talking about CCM, and I'm now concentrating on continuous current mode operation, still duty cycle, which is T on over the total period, is V out over V in, like in any buck. That is independent on the way we are generating the pulses. This always holds in a CCM condition. So in CCM, we are going to have D is equal to V out to V in, and therefore the frequency is 1 over T on plus T off. Now, as we have said, in a simple configuration, T off is going to change, and therefore the frequency is going to change. But if we'll make T on a function of V in, here it is. So V out over V in is this relationship now. T on is now a function of V in. So we find from here that T on is a function of T over V in times V out. So T on is T over V in times V out. Now, if you make T on as a function of some constant over V in, this is now T on. That is this is the dependence on V in. So this is T on equal to this. And we find that in this case, T, that is the period or the frequency, is a function of V out only. It's not a function of V in anymore. This is very nice because in a stable operation, you usually control the output. So V out is pretty much constant. V in might change, but as you can see here in this configuration, the system is not sensitive to V in if T on is chosen to be 1 over V in. So this is very, very nice. So let's have a look now at a commercial unit. As I've mentioned earlier, this is just one example. There are other companies who are making it, and in fact, Texas Instruments is making many models or many types of such controller, constant on time. And in this particular unit, there is an internal switch. This is the buck. This is the feedback. Inside is, of course, the comparator. We'll see it later on. Now, here, this is a resistor that actually set up the relationship between the T on time and V in. Okay, so it's internally controlled. Then there are some other connections here. This is just for the bootstrap. And here we have just the VCC, of course. And this is for setting the current shutdown for overcurrent protection. So here is the internal unit, and what we are interested in is, of course, we have here the switch, and then we have, this is the comparator, this is the feedback coming in here, and this is generating here the on time, as a function of this resistor R on. And so this is a fairly simple control unit that is compared to other units that require amplifier with a given bandwidth and phase compensation, etc., etc. It is a simpler configuration. So here is the data that the vendor is giving for the on time as a function of V in, and as a function of also, this is a parameter, the R on. That is, you can sort of program it. You can put R on, a certain R on, and this will dictate the relationship between V in and the on time. Now, as I've said, for good relationship, this should be 1 over V in. We don't see it here because this is log and this is linear. So if I'll plot it in a log-log scale, you see that this is indeed a linear, and the function is 44 over V in. This is in a microsecond. So this is the function. This is for a particular R1. This is for 300 kilo ohm. So you see that this is pretty much what I've said before, and the way that it is done in this particular unit in here is that the on time is programmed to change with V in, and therefore this unit should be insensitive I mean, not absolutely, but fairly insensitive to changes in V in, and we'll see it later on. Now, what about a load step? So we have a load step, and obviously, as we have a load step, we are going to see the following change. We're going to see that from the nominal picture here, constant on time, a given frequency with a given T off, it'll move in the extreme case to the maximum frequency during transient, and this frequency we have the same T on, but we'll reach T off minimum, and the T off minimum is set by the controller, so you can't go below that. So the average value of the voltage that you'll get at the midpoint here will be the T on times V in over T on plus T off minimum. This is the average value that actually you'll see here once you go into this ramping or demand for current mode. So we have an inductor. V out is about the same. Let's forget about the little drop. And here we have an average, which is new now due to the change in the frequency. So we have on the inductor a delta V, and as a result, delta I over delta V is this delta V over L, and the delta V is V average that we have found minus V out over L. So therefore the IDT is this expression. So again, as we'll have an increase in the current, frequency will go up, then it'll take a while for the current to ramp up, and the IDT, the rate at which it goes up, is dependent on these parameters. Let me just say here, sort of in parentheses, that this is a non-linear control, and the proper way to look at it is in the time domain, because in the frequency domain it really doesn't say much. I mean, injecting AC small signal and looking at the bandwidth really doesn't tell you much about what is happening within the time domain, because this is a very it's a highly non-linear system. So I think that the way to treat it is really in the time domain, and just put aside the frequency domain with the bandwidth, with the phase. It's really irrelevant to the behavior here. Well, it's relevant, but in order to connect the two, it's very complex and really doesn't lead you to anything more than you understand from what is really happening here, from this the IDT, that you can tell how fast will the converter react. As I've already said, T on is 1 over V in, then for input voltage change, then there's going to be no change, duty cycle remains the same, and you don't see any change. So how do we get the ripple? We need a ripple here, and one way is, of course, relying on the ESR or the capacitor, then you'll get the ripple. Another way is perhaps to make the capacitor small, so you get high ripple on the capacitor. Relying on ESR or relying on a small capacitor are not the best way to go, as I'll explain a little bit later. And what is usually done is either add a resistor to get the ripple here. You do need a minimum ripple for the controller to operate. You can increase a little bit the level of the ripple going into the unit, into the controller, by sort of bypassing the divider, because here you have the ripple at the output, and here you have a divider to go from the output to the feedback. This is 2.5 volt. This is the reference here, or compared to the reference. So if this is a higher voltage, then you have a higher or a stronger voltage divider. So in order to go back to the value of the ripple here, you can put a capacitor, you sort of recover the ripple here. Or, which is probably the best way to go, is to have just about no ripple here, but to add an artificial ripple, you might say, by tapping the midpoint here, or the switching point, and through this getting ripple, which is fed to the feedback, to the controller, to the comparator, but at the output you have a large capacitor. There is almost or practically no ripple. This is probably the best way to go, and it's fairly simple. It is important to realize that you cannot use a small capacitor for the ripple, and the reason is the following. If you have a resistor, a large resistor, one way or the other, or inject a ripple through some auxiliary circuitry, you have the ripple synchronized to the current and therefore synchronized to the pulses coming in. However, if you rely on the capacitor, then the ripple is phase shifted. There is a lag, and this lag can cause instability. And this will be a case of instability of constant on-time controller. So you should avoid the phase shift. You should try to get the ripple to be synchronized, the same phase as the input pulses, or also, of course, the ripple of the inductor current. So this is very important to realize. Now I'm going to show some simulation. Texas Instruments has a benchmark here of this controller, which is connected. And let's see what is happening here. This is a 5-volt output, and the input is 50 volt. It doesn't say, but that's what it is. And this is the R on. Here it's 340 kilo ohm. This is setting the on time. And then we have, this is just the VCC, and then we have this is just for the shutdown control over current protection, and that's just about it. Here at the output side, there is a load which is, well, actually the nominal is 66, I've already changed it to 100, and I've also added a current source to provide a step of 100 milliamp. And you see that they have added here to the 22 microhenry, they've added a 1 ohm resistor, so that you get a appreciable ripple here, which is, as I've said, required for the operation of the controller. Now, if you can tolerate this ripple, that's fine, there's no problem, and the ripple is not that large, we'll see it. But if you don't, then you can eliminate this resistor, put this capacitor, or even actually a larger one, and then inject the ripple with this auxiliary circuit that I've shown before. So here is an example of a step in the input. This is the input voltage from 30 to 50 volt. This is the pulses at the switching point, and this is the inductor current, and this is the output voltage. The output voltage is set to 10 volt. You see, it's a little bit more than 10 volts. And we see here very nicely the pulses. The on time is the same, of course, here. And this is with the 30 volt. And as soon as the voltage at the input goes up to 50 volt, the pulses become smaller, 1 over V in. And therefore duty cycle is left the same, and therefore you practically see no change at the output or no change in the inductor current. That's beautiful. That's very, very nice. Okay, it's sort of transparent to changes in V in. That's very nice. Now, what about changes in the load? Here is the load, and this is the change. Let me just say, first of all, that the ripple of V out, this is 300 millivolts, so the ripple is about 200 millivolts, so it's plus minus 100 millivolts. Well, in some applications it might be too much, so again, you can just eliminate the 1 ohm resistor, put just the auxiliary circuit to inject the ripple. And this is the inductor current. And what we see here is that we have a 100 milliamp step at the output, okay, in the load step. And we see here the disturbance, short time disturbance. This is just the normal frequency, and here is the disturbance, and due to this disturbance, momentarily we're going to have a ramping of the current. We see it a little bit here, very little, and we can compare it to the analytical derivation I've made, the simple one here, we have estimated the IDT to be this expression, and for this particular case, T on is about 0.7 microsecond, T off is 0.3, so it's 1 microsecond period, and L is 220 microhenry. So the IDT turns out to be 136 amp per microsecond. So therefore, with a 100 milliamp step within 1 microsecond, this should be over. Now, on this scale here, this is 5 microseconds. Okay, so from here to here, and 1 microsecond here, and indeed you see that it doesn't take much, and there's a little bit of a drop here at the output voltage. It's just estimated to be, I don't know, 50, 70 millivolt, and then it recovers and goes back to the same value. So the dynamic response seems to be pretty good. This is a low current controller. The maximum current of this controller as it is designed is about 150 milliamps. So we're talking about relatively low current, but obviously the same concept, you can of course upscale it to higher current. Another point that I'm showing here is the operation in discontinuous mode. For that, I've increased the resistor to 1K, so the current is much lower. And here it is. There's much of a difference. We see here a change in V in between 30 and 50 volt again. And as one would expect, there's almost no change even here, because the on time here is changing automatically by the controller. So in fact, the inductor doesn't know that there is a change because it sees the same average voltage. Now the voltage is higher, but the duration is proportionally shorter. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.